everyone for coming. I guess it's a bit of a chance for me to reflect on where VENSIM's come from. I certainly never expected when I came up with the visual concept of ventilation 30 years ago that we'd have a room full of people here who are dedicated users and common interests getting together to talk about it. So it's a wonderful moment for me, and I appreciate everyone who's come here today. This is a bit of a technical talk that I started a year or two ago on battery electric vehicle fires. It's a fairly contentious topic at the moment, certainly one of the major risks that's been identified, and I guess this presentation just goes through the process of how we think about them, how we model them, and I guess some of my own thoughts about where we're going with this in the future. I think later today or tomorrow, some of the outcomes of this study that I've done will be shown to be included in the next version of VENSIM, so I'm pretty excited to see that. But in the meanwhile, I just want to go through some of the theory and some of the reasons that we've included these things in the first place and how they're likely to be used. Now, there's a whole bunch of slides here. We won't have enough time to go through them all, so I'm just going to skip some of them, particularly the ones I've presented before, but there are some updates that I'd like to sort of highlight as well. I think by this stage, we know that at some stage, battery electric vehicles or zero carbon machines will become part of our future in mining. Carbon-fueled internal combustion engines have pretty well stopped in development, and I guess aftermarket solutions will still continue, but most of the major engine manufacturers are now no longer researching better engines. They're moving on to electric engines. And I think we also see legislators are continuing to introduce increasingly tough emission standards and atmospheric standards that it's going to basically drive a wedge and force the machines out of our mines. But look, the future has upsides as well. Zero emission, no DPM, no legislative vent demands, low heat relay. So there's a whole bunch of benefits with BEVs that we all recognise. And most major underground equipment manufacturers now offer some BEVs using lithium batteries, although supply, performance and safety questions still remain. There is, of course, one major downside. These things, as we know, can catch fire. We've seen plenty of examples of news reports about EVs on the surface, just normal cars catching fire. There's reports in the paper every week or two about some lithium battery fire that's happened in a city somewhere. And obviously, with these many examples of EV fires on the surface, I think we can project the same risk underground in many cases as well. So this is a real and foreseeable hazard, and it has to be managed from a risk and design point of view. This is actually one I saw in the paper a few days ago in Australia. This is a fire that was caused by an EV in a holding yard. The battery and the car had been in an accident. The battery was actually removed from the car and stored next to some other cars in the holding yard. And thermal runaway occurred in the battery, I don't know if it was days or hours later, but it resulted in every vehicle around that battery catching fire as well. And all those vehicles that you see there, they're non-EV cars, but because the battery was stored near them, they all caught fire. So we've seen a similar thing underground as well with a couple of incidents, but at this stage we don't really have enough data for underground mining to project a lot of, I guess, conclusions yet. But there are some sporadic public reports that have been made on the web. These are some I've downloaded, but I'm sure there's a lot of incidents that have happened but perhaps haven't bubbled to the surface in terms of the investigation. And so I'm very keen to sort of analyse those further as those become public. So I guess what is the risk of EV fires and how do they, what do they form such a risk to ventilation? As we know, if you look at the risk of an EV fire, sure, there's lots of incidents that happen, but there's a lot more gasoline and petrol and diesel vehicles that catch fire than EVs statistically. So even though we hear these things in the news, they tend to be greatly amplified by the media, and a petrol engine fire will just get ignored. So if you look at the statistics, and these are numbers that have been pulled out by other people, the risk of an EV fire on the surface is much lower than a gasoline or hybrid vehicle for that matter. I don't think you can take these numbers and project them to underground machines. Underground machines tend to have a lot more fire safety controls on them. They're diesel for a start. There's fire suppression systems installed. So I don't think these ratios will work underground. But that said, inherently, EVs are not necessarily more risky than other types of machines. In terms of the batteries that are used, there's a whole bunch of technologies out there. These technologies tend to be rated in terms of capacity, and the higher the capacity battery in terms of the weight, tend to be more risky in terms of fire as well. That black box there forms a bit of a summary of the major battery types that are used. Underground, you'll typically see LFP batteries, lithium iron phosphate, or NMC batteries. Those are the two major batteries used by manufacturers underground these days. There are safer technologies like LTO, but the energy density of those is really too low to be useful for most machines, but they may get better in the future. As these batteries become higher in energy capacity, the voltage of each cell in the battery tends to increase as well, and that's where you get that energy capacity. So if you want a machine that goes for a long time and it lasts a long time with a single charge underground, you need a higher battery capacity chemistry, but that can also increase the risk of fire as well, in theory. This is just a bit of a slide Epiroc put out, basically how they make their packs. They start with small cylindrical cells. They pack them together in lots of 672. They basically then bank these cells up until they get these 800 volt sub-packs of lots of these panels in series, and then they pack it together in an armoured enclosure with cooling and all sorts of other control devices to make sure it's safe to use underground. And every manufacturer has got a solution that looks a little bit like this, but some use different technologies and types of batteries as well. In terms of the batteries themselves, what can catch fire? I guess the main thing that's a concern is the electrolyte in the batteries. That's a carbon-based electrolyte. The solvent can boil and bubble and put off gas, and that gas is very flammable. You've got methane and hydrocarbons and lots of other stuff that comes off that if it catches fire. You've also got the anodes and the plastic cases that can catch fire as well. There's carbon in the batteries, and so all of those things together form the fire risk of a BEV battery. Now, under significant heat, that solvent, as I said, breaks down and you get lots of gas coming off the battery. That gas is quite flammable, hydrogen, methane, and that's where a lot of the risk comes from. In terms of how the batteries catch fire, there's a few different ways. You can obviously apply an external heat source to them, and that can spread to the battery pack once the battery pack gets hot enough. You can also start electrical fires in terms of short circuits or switches that fail, fuses that fail. And you get another phenomenon called internal battery thermal runaway, where the internal chemistry of the battery starts to short circuit itself, and the kinetic load of the electrical energy starts to create its own heat source, and you get a thermal runaway where that spreads to the entire battery and causes it to fail and catch fire. And that can result in damage or overcharging or failure of the cooling system or failure of the computer to keep the voltage of the battery at the correct voltage levels. So once that thermal runaway occurs, and that occurs at about 120 to 150 degrees, off she goes. It's like a chain reaction. The only way to stop that occurring, from propagating is to cool the battery. And typically the way that's done is just you put lots of cool water on it. You immerse it if possible. But if you don't do that, that thermal runaway continues until the battery catches fire and the whole thing burns to the ground. Now, there is a lot of misinformation about the batteries, which I'm a bit disappointed about. I won't put a name to this next slide, but this is one of the slides I saw come out from a manufacturer trying to explain how their battery is so much safer than other types of batteries. This is really misleading stuff. This is a chart that shows you the different types of gas that'll come off a battery. It sort of implies if the battery catches fire, but that's not what the test is. It's called the nail puncher test. You puncture a nail into a battery pack, and these are the gases you can expect come off the batteries. It clearly shows that LFP is a safer battery if it's punctured by a nail, whereas an NMC battery puts lots of really dangerous stuff into the atmosphere. But ultimately, putting a nail through a battery underground is probably not the likely cause of failure. Any of these battery types, if they get hot enough, or if they have a thermal runaway, will produce lots of dangerous gas. And if you put a rock bolt through a battery pack, or you put a rock on top of a battery pack, very likely all of these battery types will produce lots of dangerous gas. So just be aware when you see this sort of propaganda going around, it's not necessarily a real thing you need to consider. Sure, there's an experimental basis in this, but it's not the major risk you see with underground batteries. There's other considerations like the packaging, the BMS, the cooling systems, the armoured protection. That's just as important. In terms of the batteries themselves, when they catch fire, I need some water actually, sorry. So yeah, look, when they catch fire, they tend to be quite spectacular. There's a lot of flame and flaring and explosions. Typically, a fully charged battery will be a lot more volatile than an uncharged battery. But in terms of the total heat that comes off the battery, it doesn't really matter if the battery is charged or not. The electrolytes really drive a lot of the heat. So while a fully charged battery might be more spectacular, the same amount of heat will come off a battery whether it's fully charged or not. So when we come to the process of how do we consider these in terms of modelling, in terms of how we address the fire risk of these batteries from a design point of view, we don't look at batteries any differently than what we consider other combustibles, whether they be tyres or diesel fuel. We've got to consider three things. And they are the total heat released off the battery, the rate of heat release, and the products of combustion. So they really form the risk of your underground fire. And when we consider batteries, those are the three things we've got to calculate. When batteries burn, we've seen enough battery tests done on surface vehicles to know that they follow what's called a T-squared curve. The battery fire ramps up, it burns continuously for a period of time, and when the fuel runs out, it sort of slowly decays and burns out. So we call that a T-squared curve or time-squared curve, and it kind of looks a little bit like this. As I said before, highly charged batteries or high SOC, state of charge, tend to have a more volatile behaviour, but the amount of heat released is very similar. So when we work out the amount of heat release, just as a bit of a refresher, heat release rate is equal to the total heat released in megajoules normally divided by the time in seconds. So as an example down the bottom there, if you had a fuel source which contained 100,000 megajoules of thermal energy and you released it over 1 hour, then your heat release rate, if it was continuous for that time, would be 100,000 divided by 3,600 seconds equals 28 megawatts. That's just a picture of a Sandvik battery pack. One of the problems I've found in my research is that a lot of the manufacturers actually don't give you the weight of the batteries. They'll give you the weight of the battery module, but that module includes all of the armoured steel around the cooling systems and everything as well. So to actually get the weight of the battery, which is what you need to know to work out the thermal energy in the battery, it's actually a little bit of a process unless you've got a manufacturer who wants to volunteer that. Theoretically, the battery mass of a BEV is likely to be 10 times more or greater than the equivalent amount of diesel fuel. So if you've got a vehicle that carries 500 kilograms of diesel fuel, to get the same amount of, engine power out of the machine or engine capacity, you'll have to have a battery that's 5,000 kilograms in size. And most manufacturers can't carry a battery that big. They'll do one maybe half that size. And so that's why battery electric vehicles don't have the range of a diesel machine at this time. But that said, we're not interested in the capacity of the battery. We're interested in how much heat the battery releases. If you look at a diesel, for example, has an energy content of about 47 megajoules per kilogram of diesel fuel. If you look at a lithium battery, the combustible components of the battery, the electrolyte and the carbon and the bits and pieces, is probably more in the range of about 20 megajoules per kilogram for that battery. But the battery's got lots of stuff that doesn't burn as well. Some of the packaging doesn't burn, some of the metals don't burn as well. So you actually take the actual mass of the battery itself and it only works out to about 7 megajoules per kilogram. That said, if your battery is 10 times the mass of your diesel, that 7 megajoules becomes quite a significant heat load. And so that's why the battery mass of the lithium batteries, because they're so much heavier, in total, it puts out a very similar amount of heat than an equivalent diesel load, if that kind of makes sense. So we're not getting any more or any less heat coming off a burning battery than we are a tank full of diesel fuel. Now, because, as I said, the manufacturer's battery mass estimates are quite hard to find, I've really recommended that we actually don't look at the mass of the battery, we look at the electrical capacity of the battery if we want to work out the heat load. And through looking at some test work, and I can supply this later, there's enough experimental work to suggest that, at least for lithium iron phosphate batteries, this is a little calculation to work out how much heat load comes off the battery. So for LFP batteries, you times it by about 50, you times that by the kilowatt hour rating, and you can get the thermal heat release rate of that battery. Now, again, I don't have time to go through this in detail, but what this really shows is that whether it's a diesel tank full of fuel burning or a battery burning, the amount of heat coming off that machine is very similar. So batteries are probably not more or not less than what a diesel equivalent machine would give off in terms of the amount of energy. The only difference is if your diesel tank is empty and your lithium battery is empty, the lithium battery will still put out almost as much heat as it was when it was full. So a diesel will not, a lithium battery will. But on average, they're very similar. How do they burn? Well, they burn just as much the same as anything else that burns. It goes up, it goes across, it goes down when the fuel runs out. There's enough experiments done on surface EVs to suggest that they're going to burn very similar to a petrol vehicle in terms of the amount of time and the amount of energy that comes off those machines. Now, for smaller vehicles like these EVs that have burnt on the surface, these graphs show just normal cars that have been manufactured. They typically burn in less than 1 hour, but you put that on a large loader underground or BEV with big tyres and stuff like that, you could probably expect that to extend to 2 or 3 or 4 hours. We don't have enough data to show that for sure, but we do have data from diesel machines that show that sort of 3 to 4 hour range is a typical burn time for a large BEV. That's just a graph showing what the effect of the state of charge of the battery is. As I said, the state of charge is how charged it is. The only thing that I can show you in that graph there, you can see that the 100% charged battery has those big blue spikes. There's just gas flaring off the battery because of that short circuiting inside the battery. Now, if you measure the area under those graphs, in other words, the energy, it'll be very similar, whether it's charged or not. But that volatile behaviour when the battery is fully charged is what differentiates a fully charged battery and an empty battery. The next little thing here, and again, I don't want to spend too much time on the technical side of it, is what the gases are that comes off these batteries. And look, we're really after 2 gases which are of interest, the carbon monoxide and another gas called hydrogen fluoride. Now, hydrogen fluoride is not a common gas that we've seen before in underground. It's fairly unique to lithium batteries, and it's also an extremely toxic gas. If you look at the standards that NIOSH and other CDC put out, the standard for hydrogen fluoride in terms of immediate danger to life and health is about 30 parts per million, and for carbon monoxide, it's about 1,200 parts per million. So this is the level of gas that will cause, and again, there's a bit of a definition there, that we're really worried about the very short-term exposure of people to these gas levels. I guess what's interesting to me is I really wanted to know where this 30 parts per million came from. So I sort of dug into the NIOSH archives and I looked at where these numbers came from. And I found that most of the experiments for HF, hydrogen fluoride, were done back in the 1960s. And the way they did it is they got a bunch of animals, monkeys and rats and guinea pigs, and they gassed them, which sounds terrible, but that's what I guess they do. But they put these animals under an exposure of quite a high volume of gas, 30 parts per million, for 40 continuous hours. And not a single animal died. It wasn't until they pumped up the gas levels to about 300 parts per million that these animals started to die. And even then it took quite some time. So I get the impression that the 30 parts per million that's been put out as an IDLH, immediate danger to life and death, is quite a conservative number. It's probably because there's not a lot of statistical data on HF gassing, unlike CO, where we've got a whole history of disasters to know what that is in terms of danger. HF has got very limited medical research and exposure. So I suspect 30 parts per million is actually quite a conservative level. It's probably much higher than that, but at this stage there's not enough evidence to support that. So that's why that 30 parts per million has been put out. The short-term exposure limits, which are limits that you can be exposed for 15 minutes without injury to health, tend to be much lower. They talk about 5 or 6 parts per million. But again, they've done human test works where people have been exposed to those levels for days at a time, for weeks at a time. Human volunteers have done this, and there's been no ill health on these persons as well. So even that's a fairly conservative value. So I just wanted to caution you that on using those values. I think those values are appropriate to use because that's the best advice we have, but I don't think they have the risk, I suppose, that would be associated with carbon monoxide at that same IDLH advisory level. I won't go too much into that. These little tables here are numbers I've got from a whole bunch of experiments, and when we look at the VENSIM changes that we've made to actually model lithium battery fires, I've given all this information to the VENSIM programmers, and they've put some of these numbers in as examples. But these basically show you how much gas is generated per kilowatt hour of battery capacity, and you can use these numbers there to advise the fire simulation program in VENSIM to generate the gas levels that you might expect to see in a bad fire. So just in summary, once you know those two things, again, it doesn't have to be approached any differently than any other fire simulation in VENSIM. Once you know the heat release rate, the types of gas yields, and there's recommendations for those, you can then run a simulation of BEV fires, much the same as anything else. In terms of modelling these in VENSIM, again, I won't go through details. I'll let the VENSIM guys sort of show you how this works. But basically, we can actually define a BEV battery in the software independently, and that battery can be defined by the amount of gas that it's released per kilowatt hour. Once you have defined that, you can then put that battery into a machine that you're defining for a heat source or a fire source. You can put in the amount of battery capacity, let's say 350 kilowatt hours, and that battery then becomes part of that machine fire. And if you can choose, you can add tyres and hydraulic oil to that fire as well, so that the simulator takes all those into account and generates all those gases, the HF, the CO, the tyres, etc., etc. So it's been made as seamless as possible, and this sort of approach will help people gain some confidence, I suppose, in how to manage this, the fire risk and the ventilation design challenges for battery fires. In conclusion, as I said, lithium battery fires can be modelled within the mine via simulation software. VENSIM version 6 will have specific tools to help you do that more easily. The input should be considered a function of the battery capacity in terms of kilowatt hours, not the battery mass at this stage, until we get more information from the manufacturers. Heat release rates are similar to a typical diesel fire, so it's not necessarily going to be worse, but what may be worse is the HF gas release. That said, if a large vehicle catches fire, I think the CO is just as dangerous as the HF gas being released, and obviously you've got to take both those gases into account. You've got to obviously then, I guess, look at how you manage this gas. Obviously, HF has got very specific challenges in terms of how it's managed and the amount of fire rescue and approach you can have with this gas. The gas actually forms a hydrofluoric acid in your lungs, and that requires special filters and breathing apparatus if you want to try to fight these fires. There's going to be obviously many challenges in terms of designing mines to accommodate these sort of hazards and dangers, in particular battery storage and battery charging. These are obviously a hot spot for where fires may occur with BEVs. And in particular, the charging of these batteries and the storage of the batteries, particularly faulty batteries, is going to be a major headache for any mine that doesn't have that design already incorporated. So there's certainly lots of challenges there, but look, as I said, I'm a very pro BEV person. I believe it is the future of mining. I believe we can overcome these challenges. This is just a small part of the puzzle and helping manage the risk, I guess. But by and large, I think it is the future, and I think we can manage it with appropriate cautions and procedures and technology. So yeah, thanks for that, and hope you enjoyed the talk.
Thank you, Craig. So as usual, who has any question? There's a number of minds these days looking at BEVs. Surely there's someone who has any question on this topic.
We have one over there.
Excellent talk. Thank you very much. Question on risk. For the 100,000 vehicles right in the front, there are 25 EVs catch alight. Is that... does that take into account how many are sold? I'm just trying to understand the risk profile if you have gasoline versus EV. Is the risk of fire much lower, or is it just a function of how many vehicles are actually sold?
Yeah, no, this is for every 100,000 vehicles sold of each type, so it actually is a direct comparison of the risks between each vehicle. You can see that EVs have, 1/100th of the risk of a typical other fire, if you like, for the same number of vehicles. Yep.
So then why is there such a fuss on EV fires then? Does it not mean that that risk has always been there?
Absolutely, absolutely. But if you look at the way the media works, the media focuses on new things and things that people don't understand or trust. So EV fires will automatically get elevated to the headlines of the news. The 100 other vehicle fires will just get ignored. So I think at the moment there's a perception that EVs are dangerous and hazardous. The statistics don't back that up. As I said, though, these statistics don't translate necessarily to underground machines, which have different risk profiles. So don't take these as an underground risk. But it certainly is encouraging that perhaps they are safer than what we think.
Thanks.
Next question, Michael. Thank you.
Just a bit of a carry on with that. So we're talking about hybrid gasoline and EVs, but what about diesel? Is there any data on diesel? Because
There's
that's really
not.
the
I think these
comparison.
gasoline are actually a conglomeration of both petrol and diesel engines, and so no one's actually made the differentiation between the two. As we know, diesel is a lot less volatile, and it should, in theory, be a lot lower fire risk. And if we project that to underground diesel machines, there's even a lower risk again because of all the fire suppression and appropriate controls on underground machines. So, but no, you're right. Diesel machines, I think, would be a lot closer in terms of risk.
All right, thanks everyone for the question, and thank you, Craig, for the talk.
Okay, thank you.